geometric packing problems. And I want to convince you that using more or less one method, you can solve, well, you can try to solve, and you can get some good results on a quite a variety of geometric packing problems. So if I speak about geometric packing problems, you should think about different things, kind of packing a geometric figure into a container. For example, packing spherical caps on a sphere, or packing balls into Euclidean space, or packing pentagons into the plane, packing tetrahedra into 3 space, and so on and so on. And I want to show you one method which is useful to study all of these different packing problems. So to be more specific, I want to give you first a definition what I mean by geometric packing problem. So it's going to be, I want to study a problem kind of inspired by combinatorial optimization, independent sets and graphs, but I want to do it in a geometric setting. And I want to study independent sets in Cayley graphs. So they will correspond to my geometric packing problems. So what is it? So I want to look at the Cayley graph. A Cayley graph is a graph which is defined by a group and by a subset sigma of the group. So it's going to be a graph which is undirected, where the vertices are the elements of the group. And sigma determines the adjacency relation. So sigma, as I said, should be a subset of G, should be closed under inversion. And you should think about sigma as being the neighborhood of the neutral element. And then you have, and this neighborhood is transported by the group action to all other group elements. Formally, it means that X is adjacent to Y whenever X to the Y inverse lies in sigma. Yeah, and because I want to have an undirected graph, I want to have that the set is closed under inversion. And you also should note that the Cayley graph may contain loops. So this happens exactly when the neutral element lies in sigma. Yeah, and the simplest Cayley graph you can think of is this 5 cycle here. So it's the 5 cycle. So the group is Z mod 5Z, and the generating set is 1 and 4. Yeah, and I want to study this kind of graphs. And I want to study independent sets in these graphs. So these are just subset of the vertices, subsets of G, so that you don't have adjacent pairs inside of I. Yeah, so whenever you have 2 points, X and Y, lying in I, which are different, they should not be adjacent. And they will correspond to a valid packing. And we want to find good packings, so packings which have lots of elements. So the idea will be that we want to find independent sets in the Cayley graph which are as large as possible. But what I mean by large, and this very much depends on situation. So for example, in this case, you can simply count the number of vertices. So in this case, for example, these 2 vertices form an independent set. And then I can say, well, 2 divided by 5 is the density of the independent sets which I have here. Yeah, but the notion of largeness very much depends on G. So what are examples? So examples, I've given here 3 examples. So the first example is a finite example, where the group G is the Hamming cube, F2 to the n. Sigma is a Hamming ball of distance of radius d minus 1. So here I take the Hamming distance to define the Hamming ball, of course. And then what I do is I study error correcting codes if I want to find large independent sets in this graph. Yeah, so that's a finite graph, something which is a bit more complicated, going from finite to compact, so infinite graphs, but still to compact graphs. So this is a graph on the special orthogonal group. So the group of all orthogonal matrices having determinant equal to +1. So what do I want to study here? So what do I want to do here is I look at a spherical cap on the unit sphere. And this spherical cap is transported by the group action of the orthogonal group. And then sigma is made in such a way that if I look at spherical caps which are transported by the group, then these spherical caps should not intersect. And this forms the neighborhood of the neutral element, and this defines at the end a packing problem on the unit sphere by packing by spherical caps, which is also called the spherical code problem. So that's the compact case. Then the next step is a locally compact case. So here I have SON semi-direct product with Rn, which is a Euclidean motion group. So here I can translate and rotate things. So here I can translate and rotate my objects. And my object is a convex body K. So here I want to pack convex body K into Euclidean space, where I allow that the convex body K can be rotated and translated. Here are the pictures corresponding to the packing problems. So the first picture corresponds to the second example. I mean, the first example is not so interesting to draw because it's only interesting if the dimension is high enough. So I start with the spherical code problem. So it's packing spherical caps on the unit sphere. And here I have 3 instances of the third problem. So here, my body K, which I want to pack, is a unit sphere. So I do sphere packings. And rotation is not so interesting because the body itself is rotationally invariant. More interesting is the packing of pentagons in the plane, because here I can rotate and things really make a difference. And then things are getting more and more difficult. So here I have tetrahedra packings in 3 space, where I'm also allowed to rotate things. Yeah, so these are the geometric packing problems I'm interested in, and they all fall into the framework of independent sets in Cayley graphs. Yeah, so these are very old problems with a lot of history. So kind of just to remind you, a piece of history. So it's part of Hilbert's 18th problem to solve these problems. So he wants to study building up of space from congruent polyhedra. And then he asks, how can one arrange most densely in space an infinite number of equal solids of given forms, for example, spheres with given radii, or regular tetrahedra with given edges, or prescribed position? That is, how one can find one so fit them together that the ratio of the filled to the unfilled space may be as great as possible. In other words, part of his 18th problem is to study these geometric packing problems and to solve them. Yeah, and the ambitious goal of this talk, maybe a bit too ambitious, but we all had good lunch, and so why not? So the goal of this talk will be that we want to solve Hilbert's problem by computer using some SOS proof system. Okay. So this will not work, of course, in the talk, but I want to convince you at least of a couple of things. So the first thing I want to convince you of is that at least there's no theoretical obstruction that this could work. I will show you that if there's a proof, you can find an SOS proof for proving optimality of these structures. There is a proof. I don't say how big or how large a proof is, and I don't say how difficult it is to find, but at least there will be a proof. So at least in this SOS proof systems, the SOS proof systems are strong enough to solve Hilbert's problem for arbitrary convex bodies. Okay, and that's the first thing I want to convince you of. And the second thing I want to convince you of is that this SOS proof system also has some practical meaning, because the SOS proof system will become as a hierarchy of SOS proofs. And the first steps of the hierarchy, they give useful information for the problem. So it makes sense to study these SOS proof systems.
So you get some packing from a low rank SOS optimization?
I just give, it's about obstructions, it's about upper bounds. So I want to prove upper bounds by this SOS proof system.
You can't dualize it and get
You cannot, I don't know how to dualize it, but I think if you go, it will be an SOS hierarchy, and if you go far enough in the hierarchy, at the end, you also will have a packing in your hand. So this also kind of gives you the lower bound. But usually in practice, lower bounds are much easier to get. Look at the Kepler problem, for example. So upper bounds are the challenge, and the SOS proof systems give you upper bounds.
So it gives you better and better upper bounds?
Sorry?
So it gives you better and better upper bounds?
It gives you better and better upper bounds, exactly.
Since you mentioned it already, so what does this approach have to say about the Kepler problem?
We'll come to that. We don't solve it today, but it gives some interesting insights. Okay. Yeah.
This in the sphere packing problem, so there would also be a way to describe it without the Cayley graph, just sort of on the sphere, but you prefer the Cayley graph formulation because it allows you to do symmetry.
Exactly. I mean, I prefer the Cayley graph formulation because at the end I want to do computations. And for this, I prefer to have the symmetry at my hand. And then it's easier to kind of argue about all the problems in one way using the Cayley graph formulation. But other than that, I mean, I just want to speak in one framework about all the problems. But other than that, it doesn't buy you anything. Okay, so before I want to show you this, I mean, let's go back down to earth and see how far we can get. And then you will see that we're not so far. Okay, so I want to discuss the three problems: sphere packings, pentagon packings, and tetrahedra packings. So for sphere packings, we know from all the three problems, we have the best knowledge of the three problems, but still the knowledge is rather limited. I mean, for unit ball packings, we know that it's solved in dimension 2 because you have the hexagonal structure, and then it's not too difficult to prove that it's optimal. It's much harder to prove that this packing, for example, is optimal in dimension 3. This was first proved by Hales in 1998, and second, it was also proved by Hales in 2014. So he has two proofs. I mean, one very difficult computer-assisted proof, like 300 pages long, and then he has another computer proof, which even computer can check now. And so if you're not convinced that Hales' proof was correct, you should, in 1998, but now I think you should be really, really convinced that it's correct. So this is now dimension 2 and 3. Then there are two cases where it's almost solved, namely dimension 8 and 24, by Cologne and Hierarchies in 2003. So in dimension 8 and 24, things are very special because they have very good sphere packings, dimension 8 and 24. Dimension 8, the sphere packing comes from the E8 root lattice. And in dimension 24, it comes from the Leech lattice. And Cologne and Hierarchies, using a sum of square proof, could prove that this is optimal up to a factor of, I think, 1 plus 1 to the minus 30. So it's very, very close to optimal. And they conjecture that the sum of square proof even can prove the optimality of dimension 8 and 24, but until now they couldn't find the proof. Yeah, in lower dimensions, from 4 to 9, here's the best what we know. There the situation is not so good. I mean, lower bounds and upper bounds are kind of far apart. So the lower bound coming from constructions, from special lattices are here. Then the Kuhn-Hierarchies bound, the sum of square bound is here. And then together with David Talat, Fernando Oliveira, we could improve a little bit on the Kuhn-Hierarchies bound by using sum of squares plus some extra tricks. But still, you see, I mean, things are pretty far at all the other dimensions. Okay, this was the good case. Now let's go to the regular tetrahedra in C-space. So there was some race about good constructions around 2010. And Chen, Engel, and Glotzer at the moment have the best construction for a lower bound coming from this kind of structure. And they can show that you can fill 85% of the space by regular tetrahedra if you're allowed to rotate them. Upper bounds are not so good at the moment because simply we don't have a good method at the moment for proving upper bounds. And the upper bound by Gravel, Elsa, and Carlos, I think in a 20 pages paper, they prove the upper bound of 1 minus 10 to the minus 26. So they show it's strictly less than 1, but not so much more than that. Okay, but it just shows you how limited our knowledge is at the moment about this kind of packing problems. So we wanted to work on this. And then we thought, well, before we do the regular tetrahedra packings, we should go kind of to the easier step where we also have similar features. And then we studied the packing of regular pentagons in the plane. And then there's a construction by Kupperberg and Kupperberg son and father. And this construction of two pentagons, I mean, there's also Kupperberg mother, which also does mathematics, but she was not involved, at least not here in this paper. So that's a packing of pentagons having two different orientations, and this gives you a packing of 92%. And we could prove with our spectral methods an upper bound of 98%, so also strictly less than 1, but less than 1 than this bound. And the hope is that the methods which we use here are also useful for the tetrahedral packings. Yeah, so I asked many people in discrete geometry, I mean, if they know any upper bounds for this, but nobody could give me an answer. So we were probably the first one who kind of really studied this problem, or kind of dared to say that we studied this problem. Okay, but the method we have gives this bound, and the hope is that this bound will also transfer in some way to the tetrahedral packings.
Other regular polygons?
We could do that, but when there was some.
For example, is something like this within possibly reach for every k? Such that if you take k-gons, you're at most 1 prime minus epsilon.
If you talk about regular n-gons, then pentagons are the worst case, and otherwise. We don't know, but when things becoming rounder and rounder, and then you can go to a circle packing.
Hexagon, flying with hexagons.
The hexagons you can pack.
No. These are. No, but so you know that would be even a nicer theorem. That for every k-gon, you cannot cover more than 98% of the. For k, which is not 3, 4, and 6. So we don't return to this.
We didn't think about it, but I think we could prove that. Yeah.
Yeah, that sounds like a nice
It would be a very nice.
More questions? More ideas? Okay, so that's the situation at the moment. So we are pretty far from solving Hilbert 18 problem, even in the plane. But still the methods, because they're uniform and they give the best known results, at least they're interesting in some way. And they're also interesting for this workshop because they involve sum of squares and SDPs. Okay, so how do these SOS proof systems work? So here I gave you the SOS proof system for finite graphs. So what do? You formulate the independent set number as a polynomial optimization problem, for example, like this. And what you do is, for every vertex of the graph, you have a variable. The variable should be non-negative. It should be either 0 or 1. And you encode that it should be 0 or 1, and if it's 0, it should not belong to the independent set. If it's 1, it should belong to the independent set. And this is encoded by this quadratic equation. And then you want to maximize the sum of xc squared. So you want to have an independent set as large as possible. So that's a polynomial optimization problem. You might think that this is a redundant inequality. That's true, but this is good for us later for generalizing this problem from finite graphs to infinite graphs. What do we do now? You can set up the SOS hierarchies to approximate these polynomial optimization problem. And when you do that, you get to the t step of Lasserre's hierarchy. So that's the t level in the hierarchy. So here I write it in the primal way, kind of using pseudo moments. So here you should look at this optimization problem. The variable of the optimization problem is y. Y is a moment vector, or a pseudo moment vector. Y is indexed by independent sets I2t of independent sets of size at most 2t. Y should be non-negative. Then it should come for a probability measure. So you want to have that y empty set is equal to 1. And it should be pseudo moment. This means that if I plug y, the entries of y into a moment matrix, then this moment matrix should be positive semidefinite. So the moment matrix I've given you here. So the moment matrix of order t, there the entries are indexed by the subsets, and then you have at index j prime, you have y of j union j prime. So it's a special matrix where indices only depend on the union of the indices, where the entries only depend on the union of the indices. So this is step of Lasserre's hierarchy. And then you can prove that in the first step of Lasserre's hierarchy, you're simply dealing with the lowest theta number of the graph, or with the strengthening by Shriver, theta prime of G. So that's the first step in the hierarchy. Then you have a decreasing sequence of upper bounds, which at the end, in the alpha step, converges to the right number. So this gives you an SAS proof system for proving that, or for finding the independence number of a graph, of a finite graph. And now the idea is that we want to generalize this from finite graphs to infinite graphs. Okay. Questions? We want to generalize it from finite to infinite graphs. So the very first thing we have to do is, because we want to talk about limits, we have to define kind of a topology on the complete situation. And before that, step back. I want to say a bit more about the T-step, because in the literature, you see this is kind of the pure T-step of the hierarchy, but there are many variations possible. And for example, instead of looking at the complete moment matrix, you can look at interesting submatrices and so on. You can add some more ad hoc constraints, maybe coming from extra insights of the graph structure and so on. And to kind of speak about all these different variations in one way, I talk about endpoint bounds. And these endpoint bounds are kind of parts of Lasserre's hierarchy which make use of pseudo-moments of order at most n. So in this way, if you look at the T's hierarchy, then the T's hierarchy is a 2T bound. So the first bound, the first Lasserre 1 of G is a two-point bound, because we look at only at moments of order 2.
So an endpoint bound is always weaker than the n level hierarchy, or it could add more constraints, so it could be actually stronger than it?
Usually they're not comparable. I mean, this is just kind of, there's a zoo out of different hierarchies, and I want to speak about the zoo a bit, and so I give names to them. Okay, and now I want to generalize these bounds to the infinite graphs. Okay, so we have to need some topological assumptions. So the topological assumption I want to use is that there will be some topology on the vertex set. And look at the Cayley graphs. The Cayley graphs, they all come from some topological group, and there's some natural topology on the vertex sets. And only thing I want to have from the vertex set is that it's a house of topological space. And then I want to connect the topology on V to the adjacency relation in G. And the way I do this is I say that every finite clique in the graph, is contained in a clique which is an open set in the topology. So I think this takes a second to digest, but this is a very important kind of definition which makes things work. So for example, think about one single point. One single point is a clique. And this single point should be contained in an open clique. So there should be a complete neighborhood of this point, which is kind of a clique. And this is, of course, true for all the geometric packing problems. Because if I pack some sphere here, then the space around the sphere is completely taken, so I really have to go far from the sphere. Okay, so that's a topological restriction. And now here's a generalization. So this is Lasserre's T-step for finite graphs, and here is the T-step of Lasserre's hierarchy for this topological packing graphs. So the only thing we are doing, we replace the pseudo-moment vector y by lambda. And lambda now is not a vector indexed by independent sets anymore. It's a vector which is a Borel measure on the set I2T. So from moment vectors, we go to moment measures. Doesn't sound so good, but that's how it is. And then the other constraints are very similar to the constraints which we have here. So lambda of the empty set should be equal to 1. Then out of lambda, we can make a moment matrix using the operator AT star. I will talk about this on the next slide. This matrix should be positive semi-definite. And the objective function is lambda of all vertices of the graph. Exactly as here, where this is sum over all the vertices of the graph of y. So it's completely analogous, except that we replace this vector space here by the Borel measures. Okay, and then we have some dual formulation. So we go from measures to continuous functions. So the dual formulation is this one here. It's a minimization problem. That's the SOS side of it. And yeah, I don't want to talk about too much about this dual formulation. The only thing I want to say that there's no duality gap between these two problems. So for finite problems, it's usually easy to show. Here, it's a bit harder to show that there's no duality gap. And for actual computations, this dual formulation is also important because it is easier to solve these kind of problems, or at least it's easier to find feasible solutions for these problems. And feasible solutions will give us upper bounds for the independent cells. And here the operator AT is defined as here, and this operator, if we take the adjoint of this operator, this gives us a way to talk about moment matrices on the measure side. And then we can prove, very similar to the finite graph case, that this hierarchy converges in alpha steps. And the first step is something like the theta number, and then you have a sequence of numbers which converge in alpha steps to alpha G. In the case when G is a compact topological space. So it means that if we talk about the compact case, then this SOS framework is strong enough to prove, to solve all packing problems, in principle. But of course, if you want to do computations, then only the very first steps, Lasserre 1, Lasserre 2, maybe Lasserre 3, are really computable at the moment. But nevertheless, this framework is strong enough to solve the problems. And if you talk about the non-compact case, like Rn, then you can also use a theorem by compactifying Rn. So instead of working with Rn, you work with a Rn modulo some big lattice. Then you can apply to this torus, you can apply the theory, and then you can let the torus grow, and you will solve the problem in the limit at the end, also in this case.
What's that C? Is it M?
The C here?
Yeah.
Okay, so here in the dual formulation, K are the variables, and they should lie in this space, and C is the continuous functions on this direct product IT times IT. So C stands for continuous. And these are the dual objects in the weak star topology to the Borel measures. Okay, so that's a framework. So in principle, we can solve Hilbert 18's problem by this framework. But yeah, about explicit computations, we are not so far at the moment, but still we have some progress. So here is basically what is known for different kinds of packing problems. So packing problems starting from binary codes, circle codes, sphere packings, and convex body packings. Then 2-point bounds. The first step of Lasserre's hierarchy was computed by Delsart for binary codes, by Delsart, Goethals, Seidel for spherical codes, code L keys for sphere packings, proving almost optimality of E8 and Leach lattice. And then we could generalize this together with Fernando Oliveira for convex bodies. Then 3-point bounds have been worked out by Schreiber in 2005. So 3-point bound is some bound which lies somewhere between Lasserre 1 and Lasserre 2, probably closer to Lasserre 1, but it's strictly stronger than Lasserre 1.
Is it like triangle inequalities or something like that?
It's stronger than triangle inequalities, but they include triangle inequalities.
So there is an extension of the Lasserre theory to symmetric spaces. How are these two things related?
So the Dart theory always talks about 2-point bounds, and then it's exactly the same. The only thing, the Dart theory for symmetric spaces, it does say that the optimization problem is going to be a linear program. Here I talk about SDPs, and if the 2-point bound is going to be an SDP or a linear program, very much depends on the structure of the space. So in these cases, for 2-point bounds, this one, and that one, they're all linear programs, where this one is an SDP. And this is not a symmetric space. Symmetric spaces are exactly characterized by these bounds being LP bounds. Okay, so in circle codes, 3-point bounds were worked out by Christine Bachok and myself. And then 4-point bounds, this is kind of the furthest people could go. They were worked out by Heisweit, Mittelmann, and Schreiber a couple of years ago. And here are all things missing. But of course, this is, the table is structured in such a way that if you go down, things are getting more complicated, and if you go right, things are getting more complicated. Explains this anti-diagonal structure here. Okay. Now I want to say some things about how to compute these bounds here, the 2-point bounds for the congruent copies of a convex body. Okay, so here are general 2-point bounds for Cayley graphs. So that's the reason I focus on Cayley graphs, because then writing down Lasserre 1 is going to be a simple optimization problem. And the simple optimization problem looks as follows. So we optimize over positive type functions. So we'll say in a minute what they are. So they're functions from G to R, which have some special PSD property. Then these functions should be connected somehow to the adjacency relations. So f of x should be non-positive whenever x does not lie in sigma. And then we want to optimize this fraction here. We want to minimize f of e, f of the neutral element, divided by the integral over f over the complete group, where mu is the Haar measure on the group. Yeah, and what is
E?
E is a neutral element. Yeah, and being positive type means that I construct a matrix, and this matrix is positive semi-definite. And the construction works as follows. I take a finite number x1 up to xn elements from the group. I look at all the products, xi, xj to the minus 1. It's not going to be a matrix indexed by I and j. I plug in this product into f, and this matrix which I get should be positive semi-definite.
So you label the edges of the graph in a consistent way such that it's positive semi-definite.
Yeah, that's one way to see it. And I can do it for all the xi's. Yeah, this is, if you don't work with Cayley graphs, then you would have to optimize over matrices, or infinite matrices, indexed by the vertex set. But here, instead of a 2-variable function, it's a 1-variable function. So this buys you a lot of, this saves a lot of computations. Okay, so what we have to do now is we have to find out how these positive type functions look like. So we have to, it's easy to see that they form a cone, a convex cone, and now we want to parameterize this convex cone. So we want to parameterize this cone of positive type functions, and then we use conic optimization to solve these problems. Okay, and then we use some classics of abstract harmonic analysis to say how these positive type functions look like. And they are very much connected to unitary representations of the group. So how does it work? I can construct a positive type function when I have a unitary representation of the group. So pi is a unitary representation, kind of a homomorphism from G to the unitary group over some Hilbert space H pi. Can be finite dimensional, can be infinite dimensional, can be one dimensional. Okay, and then we have a vector h lying in the Hilbert space. And then we construct a function f of x as being the inner product of pi x h with h. And then it's easy to see that this is a positive type function. Very easy exercise. It takes 1 minute to solve. And Vallentin and Raikov in 42 proved that, in fact, all positive type functions you can write down in this form. So all positive type functions come from unitary representations. And the extreme rays of this cone of positive type functions, they correspond exactly to the irreducible representations. So if you want to optimize over this cone of positive type functions, then it's good to use the irreducible representation. And yeah, here's a kind of a very general theorem which shows a complete characterization of all positive type functions. So it gives you a complete explicit formula for producing all of them, producing all positive type functions. So in a way, it is a generalization of the Fourier inversion formula of Bochner's theorem. And how does it work? I mean, it works for nice groups G, and the groups I had before are all nice. Then I want to have that F is also nice, rapidly decreasing. And then it says that F is of positive type if and only if I can write F as this integral here. So F as this integral, and what do? I integrate over the dual group G hat, which consists out of all irreducible representations. That takes a trace of some irreducible representation pi of x times f hat of pi. So f hat of pi, these are the Fourier transform of f at pi, some d nu of pi. And f is of positive. I mean, this formula works first of all for all nice functions, but f is of positive type if and only if this f hat is a positive trace class operator. So in a sense, this is a generalization of a positive semidefinite matrix. And then if you want to optimize, what do you have to do? You have to optimize over all these positive trace class operators.
F is a function on the group. What does it mean that it's rapidly decreasing?
Then you need some differential geometry, some D-group structure on the group. In all these cases, you can make it very explicit. I mean, you need some extra structure. An arbitrary group doesn't work, but if you have a Lie group, then you can talk about rapidly decreasing. Some more words. I mean, it can happen that these things are finite dimensional. For example, if the group is compact, then the h pi's are finite dimensional, and then the integral is also an infinite sum. So it's kind of an easy thing to do. But it can happen, and it will also happen, that these h pi's are infinite dimensional objects. So back to the notation, G hat were all the irreducible unitary representation of the group. Then nu is a Plancherel measure on the group, and f hat is a Fourier transform of f. You can read off positive typeness by looking at the Fourier transform of f, and then if it's positive and trace class, then f is a positive function. So what we have to do is we have to optimize over all these f hats. And this very much depends now on the group, how these f hats look like, and how the h pi's look like. But this simply gives you a framework which works for arbitrary nice groups. Okay. So let's do this. Let's do this for the case of the Euclidean motion group in the plane. So we have to find all irreducible representations. So these are given here. Pi a are all irreducible representations. They're indexed by a, by positive numbers. And then these irreducible representations are really infinite dimensional. So they map G to the unitary group of the space L2 as 1. And L2S1 is an infinite space, so we really have to work with infinite dimensional representations. And the representation you can write down explicitly. It looks like this. So it has the characters of Rn inside. And if you work further, you see how the Segal-Mautner formula kind of specializes to this case. So you integrate over the dual group. The dual group is indexed by A, so you integrate from 0 to infinity. Then there's a Blancharel measure, which is AdA times 2 pi. There's a trace of the representation times f hat of A. And still f hat is the optimization variable. And we have to optimize over f hat, which are trace class operators mapping L2S1 to L2S1. Okay, so that's a task. Then we can write down a basis of these spaces, and then we can get everything kind of concretely in terms of polar coordinates, and then f of this in terms of polar coordinates is written in this way. So we write everything down into a basis, and the basis consists out of I, some sines, cosines, some Bessel functions, and so on. And then we have to optimize over this infinite matrices f hat of A indexed by Rs. Good. So that's a task. We want to optimize over f hat A Rs, and we want to make it in such a way that we have a positive type function. So we want to make sure that infinite matrices indexed by R and S are positive semi-definite for all A. What we did until now is we formulated kind of solving the first step in Lasserre's hierarchy in terms of an infinite dimensional SDP. And now the next goal is we want to reformulate it, and we want to relax it a bit to turn it into a finite dimensional SDP. And then we want to solve this rigorously on the computer. And the good thing is that we work with a dual formulation, so it's enough to find a feasible solution. Finding an optimal solution, I think, is rather impossible, but finding a feasible solution is possible. Okay, and then we use, again, tools from sum of squares and polynomial optimization. So what we do is we make the following ansatz. We say that our Fourier transform is of the following form, like this. So the form is that we have basically a polynomial, depending on A, times an exponential to make it rapidly decreasing. And we set a lot of these Rs to 0, because we want to make things finite. And if we do this, and we set out to the right coefficients to 0, then this forces that this function f is again a polynomial times an exponential. And then we can use tools from sum of squares to really make sure that these polynomials which come up are non-negative. And okay, so you don't have to worry about the polynomial part anymore. Sum of squares take care of this. You have to maybe wonder where the exponential part is, but this is also not a problem because the exponential part, if you look at this here, is non-negative anyhow. So it doesn't conflict with the polynomials. And then you say that, for example, that these things here, these polynomials are sum of squares, and then if you enforce this, then you enforce that the function f is of positive type. And this you can now formulate as a semi-definite program. So being a positive type function, you can, in a special class of positive type functions, you can parameterize by finite dimensional semi-definite programs.
So there are two steps of semi-definite of SOS type relaxations. First, when you go from independent set to Lasserre relaxation, and then in order to get the Lasserre certificate, you this again.
Yeah, the first part is kind of and this is just a trick to do some things on the computer. The other one is kind of a fundamental. First, this is a relaxation.
The first part is a trick to do something on the computer.
Okay, yeah, maybe. So we have two tricks after each other.
But And what's the degree of the sum of squares here?
We come to that, to the degree we use on the computer. Okay, so we can formulate now positive tightness, but we also have to look at the geometric condition. We have to see that these functions are non-positive whenever you have x not lying in sigma. And if you translate this back now to our geometric framework here, then what do you have to do? You want to have that fx comma a is non-positive if x does not lie in k minus ak. If x does not lie in the Minkowski difference between k and ak. And if a is fixed, if we think about the rotation a as being fixed, then k minus ak, if k is a polytope, is just another polytope. And in the case of the 5-gon, then k minus ak, so this is say k, the other 5-gon and the other pentagon is minus ak, then the Minkowski difference is simply this 10-gon. So for fixed a, we have a polytope condition, so we want to have that the function is non-positive outside of the polytope. And if we do the rotation now, then we have a structure like this, so it's a twisted 10-gon. And we want to have that the function is non-positive outside. And this you can also formulate as a sum of square condition. Because you can say how these faces look like, and these faces are parameterized by polynomials. Okay, then we can put everything into a computer. And then it took us, I think, 1 year to solve this problem. Because there are many numerical issues. Because, first of all, the right choice of polynomial basis is very important. I mean, if you just use a monomial basis, then things fail really bad. I mean, you don't get any results, even for very small degrees. I mean, for example, for sphere packings, if you want to work with degrees, say, 6, then solvers don't work in this case. Matrices of size 6 times 6, solvers cannot handle at the moment.
You know the reason?
Condition numbers.
Condition.
And then after playing a lot with this basis, we found out that the right choice, or our choice, was that we take Laguerre polynomials appropriately scaled as a polynomial basis. And this works well. And then we could solve these optimization problems using the software SDP GMP up to D 51. But the degree was actually twice this. So we could work with polynomials of degree 100. And then to make really rigorous computer proofs at the end, because the SDP GMP just gives us floating point solutions, so we really have to make a rational certificate out of it. So what do? We do a lot of post-processing. So we take this floating point number, we perturb it to a rational solution. Then it's not a solution anymore, because it will either not be PSD or it will not satisfy all the equality constraints. Then we analyze the equality loss of this perturbation by looking at eigenvalues and condition numbers. And then after we do this, we are at least sure that in the neighborhood of this rational solution, which is not a solution, there is a solution. And for doing all this, we had to write some custom-made C++ library, which works for SCPs with SOS constraints. Okay, so this is all the work we did for the pentagons. So how does it look for tetrahedra?
You know, for example, this choice of Laguerre polynomials is optimal in some sense, or
We don't
just
know.
a trick that worked?
It's just a trick that worked. It's not so surprising because these Laguerre polynomials also come up in the Fourier transforms. But we don't really have a reason at the moment.
Are there some other scaled polynomials that you tried? Or
We tried like Chebyshev polynomials, which didn't work.
Legendre, Gegenbauer, etc.
Yeah, we tried all these. The Laguerre polynomials, I think, work because we are dealing with a non-compact domain. And the zeros of these Laguerre polynomials, they go to infinity if the degree goes to infinity. And this is not true for the other cases. Tetrahedra, we're not there yet. So we think we need more automatization, also in the formulas on harmonic analysis. So we have to kind of find a way to make these formulas correct. Then we really have to find a way to do numerical optimization in a stable way. So just playing with Laguerre polynomials and hope that it works. I think this will not work for tetrahedra, and I think it's still a challenge.
Questions and comments for
do you think that these methods might generalize to packings in complex spaces?
Complex spaces?
Complex spaces, like I'm interested in packing lines in complex projective space.
Yeah, sure. People also worked this out. Packing in projective spaces, complex projective spaces. I mean, there's a 2-point bound, and people worked this out. And it's not too complicated. Also, 3-point bounds have been worked out.
By the same packings on manifolds.
Principle, yes, but if you want to do computations, you have to get kind of the Fourier analysis in it at your hand. I mean, you have to make things explicit. And if you don't have a good group structure, then things are getting really complicated.
Semi-groups.
Semi-groups. Sorry.
Like some of the positive type functions here, etc., all exist on semi-groups actually. So
We didn't look at that.
So is it conceivable that this can solve the problem? That this approach can solve the Kepler problem?
You say that maybe in the 4th step of Lasserre's hierarchy, you get the optimal solution. Could be. I don't know. But I think it's very hard to compute this.
But you don't know an implicit obstruction that.
Yeah, and I think there's no principal obstruction. I mean, if you go far enough in the hierarchy, you will get the Kepler problem. And you will solve the Kepler problem.
In
So
a
is this
finite,
exactly that? Is this a theorem that there is a finite number?
For the non-compact case, I think you can do that. I mean, you first have to prove that the optimal structure will have some finite complexity. And I guess in 3-dimensional space you can do that. And once you have that, I think you can use this machine. But I think then you also borrow a lot of things out of Hell's proof before you.
Good. Let's thank Frank.